Welcome to Agentic AI World, your daily interview prep for senior AI engineering roles. Episode 85. Today's topic, AI Self-Supervised Learning Deep Dive, how senior engineers master label-free representation learning in modern AI systems. Let's get into it. What is self-supervised learning? Self-supervised learning, or SSL, is a training paradigm where a model learns representations from unlabeled data by solving a pretext task. A task where the labels are automatically derived from the data itself. Think of it this way. Instead of hiring humans to label a million images, you let the data label itself. The model learns by predicting parts of the input from other parts. No expensive annotation required. This is how GPT learns language. This is how BERT learns context. This is how CLIP learns vision language alignment. Self-supervised learning is the backbone of modern foundation models. Why does it matter in interviews? Senior AI roles at top companies, Google DeepMind, OpenAI, Metafair, Microsoft Research, will probe your understanding of self-supervised learning in several ways. 1. System design. How would you pre-train a domain-specific LLM on proprietary company data? The answer is self-supervised learning. 2. Architecture questions. What's the difference between masked language modeling and causal language modeling? That's comparing BERT-style SSL with GPT-style SSL. 3. Production considerations. How would you build a self-supervised pre-training pipeline that scales to 1 billion tokens? Now you need to think about data pipelines, distributed training, and checkpointing. Know these answers cold. The 4 families of self-supervised learning. Let's break down the major categories. Each has distinct interview relevance. Family 1, predictive methods. These methods predict one part of the data from another. Masked language modeling, MLM, is the BERT approach. You randomly mask 15% of tokens and train the model to predict the missing ones. The key insight: to predict a masked word, the model must understand bidirectional context. It reads the full sentence, left and right, before predicting. Causal language modeling, CLM, is the GPT approach. Predict the next token given all previous tokens. No masking, just left to right prediction. Simpler, but scales incredibly well. GPT-4, Claude, Gemini, all trained with causal language modeling at their core. Image and painting is the vision equivalent. Mask a region of an image and predict the pixels. MNE, masked autoencoders, by he et al. At Meta does exactly this, masking 75% of image patches and reconstructing them. Family 2, contrastive methods. Instead of predicting missing content, contrastive methods learn by comparing. The goal: pull representations of similar views together, push dissimilar ones apart. SimCLR from Google Brain is the classic example. Take an image. Create 2 augmented views. Crop, rotate, color jitter. A good representation should map both views to nearby points in embedding space. A different image should map far away. MoCo, momentum contrast, from Facebook AI improves on this with a memory bank of negative examples, making contrastive learning practical at large scale without needing a huge batch size. Contrastive methods are powerful, but have a key weakness: they need negative examples. Without careful design, the model collapses, mapping everything to the same point. Family 3, self-distillation methods. These methods are collapse-free alternatives to contrastive learning. No negative examples needed. BYOL, bootstrap your own latent, uses 2 networks, an online network and a target network. The online network learns to predict the target network's representation of a different augmented view. The target network updates slowly via exponential moving average. No negatives, yet no collapse. DINO from Meta extends this idea to vision transformers. The student network learns to match the teacher network's output on different crops of the same image. DINO produces remarkable semantic representations. It learns object segmentation without any segmentation labels. Family 4, generative methods. These methods train an encoder-decoder to reconstruct the input from a compressed latent representation. Autoencoders compress data into a bottleneck and reconstruct it. Variational autoencoders add a probabilistic latent space. Masked autoencoders, ME, take this to vision transformers, masking most patches and reconstructing them. The difference from predictive methods: generative methods typically reconstruct the raw input, pixels, tokens, while predictive methods may predict abstract representations. Pretext tasks, the core design challenge. The quality of self-supervised learning depends entirely on the pretext task. A good pretext task forces the model to understand the data's underlying structure. Bad pretext tasks lead to shortcuts. If you ask a model to predict image rotation, it learns rotation equivariant features, useful but limited. If you ask it to reconstruct masked patches at high resolution, it learns rich spatial and semantic features.